In this video, we're going to look at another example of using an iterated integral to evaluate a double integral over a general region. So we're being asked to do the double integral of 6x squared dA, where our region is bounded by the curves y equals x cubed, y equals 2x plus 4, and x equal to 0. Now, looking at the integrand, 6x squared is easy to integrate whether it's with respect to x or if it's with respect to y. So that really doesn't help me choosing an order of integration. However, if we decided to try to integrate with respect to x first, that means we hold y constant, and we would need bounding curves for x in terms of y. Well, notice as your y's go from 0 to 4, your bounding curves go from x equal to 0 to x equals cube root of y. However, when we go from 4 to 8, we go from x equals y minus 4 all over 2 to cube root of y. Now remember again, the reason why I've changed those to functions of y is if I chose to integrate with respect to x first, I need the bounding curves as functions of y, or in terms of y. Since that leftmost bounding curve changes, we would need to use two iterated integrals to calculate the double integral, and that doesn't sound like something we want to do. Notice instead, if we integrate with respect to y first, then I hold my x constant, and I can use the same bottom bounding curve and same top bounding curve throughout the region. So that's why we'll choose to integrate with respect to y first and then with respect to x. So when we set it up, our bounds for y will be between x cubed and 2x plus 4. Our bounds for x will be 0 to 2. 6x squared is easy to integrate with respect to y because it's just a constant as far as y is concerned. We get 6x squared y. If we plug in our endpoints and simplify, we should get the function 12x cubed plus 24x squared minus 6x to the fifth, and we're integrating that from 0 to 2. Antiderivative for that is 3x to the fourth plus 8x cubed minus x to the sixth, and when we plug in our endpoints and simplify, we should get 48.